we present our neural-preconditioned solver for Poisson equations with mixed boundary conditions. One important application of Poisson equations is incompressible fluid simulation. In this case, incompressibility implies divergence-free velocity. Here are a list of equations that must be satisfied for incompressible fluid. There exist two boundary conditions, Dirichlet and Neumann. Solving the incompressible equations involve three steps: advection, pressure solve, and projection. And the pressure solve is the most expensive part. With the standard 5-point stencil finite difference discretization, it reduces to solving a discrete Poisson equation. For large-scale problems, it yields a large linear system, which is also ill-conditioned. Moreover, finding an effective preconditioner to iteratively solve those systems is extremely challenging. Even the state-of-the-art solvers are suboptimal for this problem. We will demonstrate that our neural preconditioner can outperform the state-of-the-art methods like AMGCL, AMGX, as well as recently proposed neural preconditioners. Although some machine learning solvers were proposed to tackle incompressible fluid simulation problems, they are slower than unpreconditioned CG, which makes them impractical for real-time simulation. Moreover, their solvers can only address Neumann boundary condition, whereas ours is capable in mixed boundary conditions. Our neural preconditioner is paired with an iterative solver. At the beginning of each step, we apply neural network to obtain a search direction. Then we orthogonalize it over previous search directions. Lastly, we compute an optimal step size and update the solution. Our network was motivated by multigrid structure, which constructs a hierarchy of coarsened grids. We use average pooling and upsampling in place of restriction and prolongation. For smoothing effects, we adopt custom convolution with spatially varying kernels. This custom convolution is crucial for the performance of our network. For the standard convolution, the same kernel is applied everywhere, whereas for our custom convolution, the kernel is inferred from the corresponding window in the image. Our training data were obtained from simulation examples, including 183 matrices, each with 800 right-hand sides. Each 800 right-hand sides were generated from 1600 Ritz vectors. The residual 2 norm was adopted as our loss function. We benchmarked on a total of 2,400 linear systems, from 12 simulation scenes. We compared our solver to AMGCL, AMGX, incomplete Cholesky, as well as DCDM and FluidNet whenever possible, using unpreconditioned CG as the baseline. We run all the solvers until residual is reduced by 6 order of magnitude. The horizontal axis is speed up over CG, greater than 1 implying faster than CG. The vertical axis is fraction of systems corresponding each speed up range. Our solver is on average 6 times faster than the baseline, and the fastest solver for 96% of all the examples. It is even more effective on larger systems. FluidNet and DCDM do not apply to mixed boundary and often run out of GPU memory on large systems. Our speedups are also greater on Neumann-only examples, with more than 20 times speedup on some large problems. Note that DCDM is slower than CG on the left. We also rendered some simulations from the test examples. Thank you for watching.